Okay, so in this video, let's try to solve a dual combustion cycle. Okay, so first thing that we need to do, as we do always, so draw the PV and TS curve. So in the PV diagram, so let's label the processes. So we have the isentropic compression, constant volume heat addition, then constant pressure, then isentropic expansion, and as well as constant volume. Okay, so in heat addition, we've said in the previous video, heat addition is occurring twice, wherein it is added from point 2 to 3 and 3 to 4. Okay, so the first thing that we need to do is to write our given. So with the problem, we are given the mass, which is 1 pound mass of air. So we know that air is 53.34 or 53.35 will do. Foot-pounds per pound mass Rankine. And then P1, so that is at the suction, we have 14.1, so PSIA. And T1, that is 80, so plus 460, that is 540 Rankine. So the compression ratio, so we are given the compression ratio RK, that is also equal to V1 over V2 equal to 9. So the pressure at the end of the constant volume heat addition, so the pressure at the end of, so let's say that the end of the constant volume heat addition, that is, this is the constant volume heat addition. So at the end of it now, so it has 470, so that is 0.3. Okay, so we have P3 is equal to 470 PSIA. So there are 100 BTU added during constant pressure expansion. So that is QA, or heat addition, at points 3 to 4. So that is 100 BTU. Right? So here, so let's disregard the A, B, C, D, and E. So let's try to solve for the entire cycle. PVT, so that is the PVT of all the points, pressure 1, 2, 3, 4, and volume 1, 2, 3, and 4 until 5. Okay, so let's try to solve for all of them. Okay, including this one, of course. Okay, so now we forgot. So this is air. So air has a specific heat ratio of 1.4. So if in the problem it doesn't necessarily states that the air is hot air cycle. So if hot air cycle K is 1.34 or 1.3. However, if it doesn't mention any, so you can assume that is a cold air cycle, or that is 1.4. Okay? So let's start first with point 1. Okay? So actually, I am given mass, pressure, and temperature. So I have R. So the first thing I can solve is I can solve for V sub 1. Okay? So actually I can solve for V sub 1 using the equation of state. That is V1 is equal to M R T sub 1 over P sub 1. So the mass is 1 pound mass times R, which is 53.34. That is in foot-pound per pound mass Rankine, times T sub 1, that is 540. Okay, over, so in the denominator we have P sub 1, which is 14.1, so that is PSIA. So we need the conversion factor of 144 inches squared or feet squared. Okay, so by cancelling the unnecessary units, so we have pound force, inches squared. So we have feet squared and feet. So if you multiply them, you will have feet cubed. Okay. So V1 is equal to, so we have 1 times 53.34 times 540 divided by 14.1 times 144. So we have the volume, which is 14.186 feet cube. So So let's rewrite this one. So this one should be 14.1. Okay, so let's put an underline here. Next, so now I have obtained V sub 1. So since I have the compression ratio, I can also obtain for V sub 2. So that is letter B. Okay, letter B. So V sub 2 is equal to, that is V sub 1 over RK, or your compression ratio. So we have 14.186 feet cubed over compression ratio, which is 9. So we have V sub 2 is equal to, so divided by 9, so we have 1.576 feet cubed. Okay, so as we mentioned before, V2 is equal to V3. So for letter C, we can conclude that V3 is equal to V sub 2, wherein V3 is also equal to 1.576 feet cubed. Okay? Next. So now we have V1, P1, and T1, so we're good already with point number 1. Now, let's proceed with point number 2. So in point number 2, we only have V sub 2. So we need to solve for P2 and T2. So that is letter D. So we need to relate P2 and P1 isentropically. So that is P2 over P1. So that is equal to V1 over V2 raised to K. So P2 is equal to P1, that is 14.1 PSIA, times RK. So V1 over V2 is RK, so that is 9 raised to 1.4. So as you can see, P2 shall increase. From point number 1 to point number 2, it shall increase. Okay, so the value that we need to solve here should be greater than 14.1. So we have 14.1 times 9 raised to 1.4. So we have the pressure of 305.6. That is in PSIA. Okay, so that is P sub 2. Next, how about T sub 2? Letter E. So T sub 2, we can solve it also using isentropic relation. Okay, so we have T sub 2 is equal to T sub 1, that is 540, times 9 quantity 1.4 minus 1. So T sub 2, based on our TS curve, should increase. Okay, from point 1 to 2 shall increase. Okay, so we have 540 times 9 raised to 1.4 minus 1. So we have 1,300.44. That is in Rankine. Okay, so we have PVT of point number 2. So let's proceed with point 3. So in point 2 and 3, we need to relate them isochorically or isometrically. So constant volume process. So we will use P2 V2 T2 is equal to P3 V3 T3. Okay? So that is a constant volume process wherein we can cancel the volumes. So we will have T3 over T2 is equal to P3 over P2. Okay? So P3 over P2, as you can see, that is your pressure ratio. Okay? So since we are given already P3 and P2, okay? So P3, that is 470 and P2 is 305. So in letter F, let's try to solve for the pressure ratio. The pressure ratio, that is, so P3, that is 470 PSIA over 470 over 305.6 PSIA. So this two will cancel out, leaving us with the pressure ratio of, so we have 470 divide by 305.6. So we have 1.537. So 1.537. Okay, so this is our pressure ratio. Okay, so pressure ratio is a necessity, so therefore we need to box this one. Okay, so this one is a necessity. So what are other necessities here? So percent of clearance. So now we have the RK. So in letter G, we can solve for the percent clearance using RK is equal to 1 plus C over C, wherein we can solve for C here. So this will become cross multiply this. We have RK times C equals 1 plus C. Then isolate, we have RK times C minus C is equal to 1. Then C quantity RK minus 1 is equal to 1. Then divide both sides by RK minus 1. So we have C is equal to 1 over RK minus 1, or 1 minus RK, that is 9 minus 1. So that is 1/8. So that is 0.125. Okay, so that is C should be 0.125, or simply 12.5%. Okay, so that is your clearance. Next, okay, so now we solve RP, so we can solve for T3. So that's letter H. So we can solve for T3. That is T3 is equal to T2 quantity, the pressure ratio. Okay, so T sub 2, that is 1,300.44 Rankine times the pressure ratio of 1.537. So T3 is equal to, so that is 13.44 times 1.537. So we'll have 1,998.77. That is in Rankine. Okay. So we have P3 and T3. So T3, then P3 is given, V3 is equal to V2. So we have that. So now we can proceed with letter I. That is point number 4. Okay. So in point number 4, so we can solve for pressure here. So pressure is constant. So pressure 3 is equal to pressure 4, or simply pressure 4 is equal to 470 psi. Okay. Next, letter J. So T4, so we can solve for T4. So we've said that it is a isobaric. So that is 3 times P4 V4 T4. Okay, so it is isobaric, so therefore pressure will cancel out. So if we perform separation of variables, we will have T4 over T3 is equal to V4 over V3. Okay, so V4 over V3 is your cutoff, so we don't have V4, we don't have T4, and we don't have how many unknowns here? So V4 is unknown. Yes, it is unknown, and T4 is also unknown. So therefore, we cannot immediately solve for this one. We need to utilize the given equation, which is the heat added in 3 to 4. Okay, so in heat added to 3 to 4, that is QA from 3 to 4, wherein it occurs at a constant pressure. So QA, that is equal to 100 BTU. So we can solve for this one. We can immediately solve for T sub 4. Okay, so here, so this is heat, so that is QA is equal to constant pressure MCP T4 minus T3. So CP, we don't have yet CP, but we can solve for it using CP is KR over K minus 1, which is 1.4 times 53.34 over 1.4 minus 1. So CP is equal to, so that is 1.4 times 53.34 times 1.4 minus 1. So 186.69. 0.69 foot-pound, pound mass, Rankine. Okay? So let's rewrite that. Okay? So here, we can solve for T sub 4. So let's divide both sides by MCP and then transpose T3. So we have T4 is equal to QA over MCP plus T3. So QA, that is 100 BTU. So we need the conversion factor here. We have 778.16. That is foot-pounds per 1 BTU. Over M. So mass is 1 pound mass. So 1 pound mass is given in the problem. So assuming conservation of mass. CP, that is 186.69. So foot-pounds per pound mass Rankine plus T3. So T3, that is 1998.77. So 1998.77. So by performing dimensional analysis, BTU, pound mass, foot-pound force, cancel. We have T4. Okay? So in T4, based on our TS diagram, from point 3 to point 4, it shall increase as well. Okay? So here, if we solve for T sub 4, that is 100 times 778.16 divided by 1 times 186 86.69 plus 1998.77. So we have 2415.58. So that is in Rankine. Okay? So this is T4. Now we have T4, letter K. Letter K. So we can solve for V sub 4. So we have V sub 4 from this equation. So we have V4 is equal to V3 times T4 over T3. Okay? So V3 is 1.576 times, let's put the unit. So that is in feet cube times T4, that is 2415.58 over 1998.77. So the Rankine here will cancel. We will have V4 is equal to, so V4 from V3 to V4, so it should increase. Okay? So from 1.576, it should have a greater value. So we will have 1.576 times 2415.58 divided by 1998.77. So this is equal to 1.9046. 046, that is in feet cube. Okay? So now we have V4, that is letter L. We can solve for the cutoff ratio, which is given by V4 over V3. So V4 is 1.9046 all over, so that is in feet cube, all over V3, that is 1.576. So feet cube. So let's cancel feet cube. We have the cutoff ratio of, so this one divide by 1.576. So 1.208. So that is our cutoff ratio. So we need to put a box to this one because this one is a necessity. Okay, so what do we have already? So we have this 3. So the next one, so you have V4, T4, P4. Okay, so now, so letter M. So we now proceed with point number 5. So in point number 5, so we need to relate it to point number 4 isentropically. Okay, so we can rewrite them as T5 over T4 is equal to V4 over V5 raised to K minus 1. Okay, so T5, so we have T4 already, which is 2,415.58 times V4, that is 1.9046, and then V5, so we've said earlier, so V5 is equal to V sub 1. So here, so we can conclude it here. So this one is also equal to V5. Okay, so 14.186 feet cubed. So that is raised to 1.4 minus 1. So the temperature shall decrease because as we've said, so you are from point 4. So the highest temperature of your cycle in dual combustion is 0.4. So from 4 to 5, so 0.5 should be relatively lower compared to T4. So we have, so if we solve for this one, we will have 2415.58 times 1.9046 divide by 14.186, quantity 1.4 minus 1. So we will have 1081.929. So T5 is 1089, 81.929. So let's get 3 decimal places. Okay, so this is in Rankine. So we have T5 already. So let's generate a separate section, letter N. So for V sub 5, so we've said that V1 is equal to V5, so therefore V5 is equal to 14.186 feet cube. Okay, next, so letter O. So in letter O, so we have V5, T5, so what we need is P5 over P4 is equal to V4 over V5 raised to K. So P5 is equal to, P4 is equal to 470 PSIA times V4, that is 1.9046 feet cube over 14.186 feet cube, quantity 1.4. So P sub 5, so let's consult again the PV diagram. So P5 should be relatively smaller than P4 because the high pressure is already converted to useful work. So we have P5 is equal to, so we have 470 times 1.9046 divided by 14.186 raised to 1.4. Okay, so that is 28.263 PSIA. Okay, so that is our P5. So that is relatively lower than 470. Next, so now we have P5, T5, and B5. So we are now ready to solve. So that is letter P. We are now ready to solve for QR, or heat rejected. So heat rejected occurs at constant volume. So that is negative mCV T4 minus T1. So CV, we can solve for that using CV is equal to R over K minus 1. So R is 53.35 over 1.4 minus 1. So CV is equal to, so that is 53.35. So that is 53.35 minus divided by 1.4 minus 1. So that is 133.375. So that is in foot-pounds per pound mass Rankine. So we can substitute this in the equation since we have T4 and T1. So we have QR, that is equal to negative 1 pound mass. So 1 pound mass times CV, that is 133.375. So foot-pounds per pound mass Rankine times T4. This should be T5. Okay, so because we have fifth point. Okay, so T5, that is 1081.929 minus T sub 1. So T sub 1 is 540. So 540 Rankine. Okay, so we have pound mass, Rankine. So since this one, so we need to convert that in terms of BTU. So we have QR is equal to, so once we've solved for the linear equation, let us convert it in BTU. So we have 133.375 times 1081.929 minus 540. So that is 72,000. So let's divide it by 778.16. So we have heat rejected, that is negative 92.88 BTU. Okay. Next. So this is letter P. So Q. So Q, we haven't yet solved for the heat addition in points 2 to 3. So that is during constant volume process. Okay, so that is QA is equal to mCV, that is T3 minus T2. So mass, that is 1 pound mass, times CV, that is 133.375 foot-pounds per pound mass Rankine. So this is pound force times T3, 1998.77 minus T sub 2, that is 13.44 Rankine. So Rankine and pound mass will cancel, leaving us with QA from points 2 to 3 is equal to, so we have 1 times 133.375 times 1998.77 minus 13.44. So we have 93,000 divided by 778.16. So we have 119.69. 0.69, so that is BTU. So let's get the third decimal. So 2, 692. Okay, So by obtaining that, so we can solve for the total heat added of the system. So that is heat added of the system, that is total of QA from 2 to 3 plus QA from 3 to 4. So QA from 2 to 3, that is 119.692. That is in BTU, plus 100 BTU. That is from 3 to 4. Okay, so this one. So QA of the system, that is equal to 119 plus 100. So we have 219.692. 692 BTU. Okay, so that is the total heat added of the system. So now we have QA and QR. So that's letter S. So we can solve for the work net. That is QA of the system minus absolute value of QR. So QA, we've said that is 219.692. That is in BTU. Minus the absolute value of the heat rejected, that is 92.88 BTU. So the work net of the cycle is equal to, that is minus 92.88. So that is 126.812 BTU. Okay, so it's not a necessity as well. So this one is a underline. Okay. Next, so now I have the work net, so letter T. So I can solve for the efficiency. That is work net over QA. So that is 126.812 BTU over QA, that is 219.692 BTU. So this one will cancel out. So the efficiency should be, so that is 126 divided by 219.692. I have 57.72, 0.5772, or approximately 57.72%. Okay, so this one is the efficiency of the cycle. So if you want to check that, so we can use the shortcut, that is E is equal to 1 minus 1 over RK raised to K minus 1. So quantity RP, RC raised to K minus 1 over, so this one should be RC minus 1 plus K quantity KRP quantity RC minus 1. Okay, so we have 1 minus 1 over, our compression ratio is 9, then raised to 1.4 minus 1 times RP, our pressure ratio, that is 1.537 times RC, our cutoff ratio, that is 1.208 raised to 1.4 minus 1 all over. So this one should be RP, not RC. Okay, so this one should be RP. Okay, so RP, that is 1.537 minus 1 plus 1.4 times RP, that is 1.537. Quantity, the cutoff ratio, that is 1.208 minus 1. So let's try. So the efficiency is equal to 1 minus 1 over 9 raised to 1.4 minus 1. So times 1.537 times 1.208 raised to 1.4. So that is minus 1. Divide by 1.537 minus 1 plus 1.4 times 1.537 times 1.208 minus 1. So this should be equal to 0.5772, or approximately 57.72%. So it corresponds as well to the long method. Okay? So this one is also valid. Next. So letter U. So in letter U, we need to solve for the volume displacement. Volume displacement is V1 minus V2. And V1 is given by 14.186. That is 14.186 feet cube minus V sub 2. That is 1.576 feet cube. So the volume displacement, that is equal to, so 14.186 minus 1.576, that is equal to 12.61 feet cube. Okay. Next, letter V. So the last one is for us to solve for the mean effective pressure, which is given by work net over volume displacement. Okay, so check on the efficiency. So the next is the mean effective pressure. Okay, so we have the work net of 126.812 BTU over volume displacement of 12.61 feet cube. So we have a conversion factor in the numerator. We have 778.16. So that is in foot-pound force per 1 BTU. So we can cancel BTU and foot. So we have 2 on the denominator. So the mean effective pressure, this is equal to pounds per feet squared. So we have 126.812 times 778.16 divided by 12.61 equals, so this is in PSF, so let's divide it by 144. So we have the mean effective pressure of 54.344. So that is in PSI. Okay? So as you can see, in dual combustion cycle, we have almost completed the entire alphabet because of the added point or the added state in the cycle. However, the process is still the same. So the equations are still the same. However, you need to be familiarized with the changes, especially with the simplified equation of its efficiency. Okay? So I hope that we obtained the same answers in the problem. So if you want to try it on your own, so feel free to pause the video. So if you want to try it again, so let's say you have different answers than mine, so you can try to solve the problem again, then you pause the video first and then you try solving it on your own. Okay? So I hope you've learned something with regards to dual combustion cycle. So thank you for watching and stay safe for everyone.